This video covers Part 1 of Section 3.3, Algebraic Structures. An algebraic structure in mathematics consists of a set together with one or more operations defined on the elements of the set which satisfy certain properties or axioms. For instance, on the set of integers, z, we have defined the operations of addition and multiplication which satisfy the following properties, among others. The first is closure under addition, which states for all a, b, and z, a plus b is in z. So the sum of any two integers is also an integer. Second, the associative law of addition. For all a, b, c, and z, a plus the quantity b plus c is equal to the quantity a plus b plus c. And third, the commutative law of addition. For all a, b, and z, a plus b is equal to b plus a. So the commutative law tells us that it doesn't matter in what order we add two integers. The associative law tells us that when we're adding three integers, it doesn't matter whether we add the second and the third, and then the first, or the first and the second, and then the third. The fourth property is existence of an additive identity. And this states that there exists an element, namely 0 in z, such that for all a in z, a plus 0 is equal to a. So 0 is called an additive identity for the set. Fifth, existence of additive inverses. For each a in z, there exists an x in z such that a plus x is equal to 0. So x is an additive inverse for a. 6. Closure under multiplication. For all a, b in z, a times b is in z. So when we multiply two integers together, we get back an integer. 7 is the associative law of multiplication. For all a, b, and c in z, a times b quantity times c is equal to a times the quantity b times c. And 8 are the two distributive laws. For all a, b, c, and z, a times the sum b plus c is equal to a times b plus a times c. And the second one states a plus b quantity times c is equal to a times c plus b times c. Now there are other properties that the integers satisfy, but we're only going to focus our attention on these 8. It turns out that there are other algebraic systems that share the fundamental structure of the integers. That is, there are other sets on which we can define an addition and multiplication which satisfy these same 8 properties as the integers. This suggests that it might be productive to abstract the common features of such systems to develop a general theory that can be applied in all such cases. For instance, the set of polynomials with integer coefficients has an addition and multiplication that satisfy the same 8 properties as the integers. The set of 2 by 2 matrices with real entries also has an addition and multiplication that satisfy these same 8 properties. Instead of deriving results about each of these sets, the set of integers, the set of polynomials with integer coefficients, and the set of 2 by 2 matrices with real entries separately, we define an abstract algebraic structure which encompasses each of these individual systems. We can then derive results about the abstract structure which can be applied to each individual system. In the following definition, we define a ring, which is the abstract algebraic structure modeled after the properties of the integers. So a ring is a non-empty set R together with two operations, addition, which is denoted with our usual plus sign, and multiplication, which is denoted with a dot, that satisfy the following axioms. The first is closure under addition, and we'll denote this by R1, and this says for all a, b, and r, a plus b is in R. The second axiom, R2, is the associative law of addition. For all a, b, c, and r, a plus the quantity b plus c is equal to the quantity a plus b plus c. Third is the commutative law of addition, R3. For all a, b, and r, a plus b is equal to b plus a. Fourth, or R4, is the existence of an additive identity. And this states there exists an element 0 sub r in R such that for all a in R, a plus 0 sub r is equal to a. And we're going to denote the additive identity by 0 sub r because it may not be 0. And this statement has symbolic form. There exists a 0 sub r in R such that for all a in R, a plus 0 sub r is equal to a. And again, the element 0 sub r is called the additive identity for the ring. R5 is existence of additive inverses. For each a in R, there exists an x in R such that a plus x is equal to the additive identity 0 sub r. And this statement has symbolic form. For all a in R, there exists an x in R such that a plus x is equal to 0 sub r. The element x is called the additive inverse of a. R6 is closure under multiplication. For all ab in R, a times b is in R. R7 is the associative law of multiplication. For all a, b, c in R, quantity a times b times c is equal to a times the quantity b times c. And R8 are the two distributive laws. For all a, b, c in R, a times the sum b plus c is equal to a times b plus a times c. And the second is the sum a plus b times c is equal to a times c plus b times c. According to our previous observation, the set of integers z with the usual addition and multiplication is a ring because it satisfies these 8 axioms. To show that any other set R with 2 operations, addition and multiplication, is a ring, we need to verify that the 8 axioms contained in the definition are satisfied. For axioms R1, R2, R3, R6, R7, and R8, this involves proving a universal statement is true. Axioms R4 and R5 involve statements with mixed quantifiers. Note in particular the difference in structure between axioms R4 and R5. In R4, existence of an additive identity, which is there exists a 0 sub r in R such that for all a in R, a plus 0 sub r is equal to a, the existential quantifier comes before the universal quantifier. This means we have to find one element, 0 sub r, such that for all a in R, 0 sub r plus a is equal to a. The additive identity element 0 sub r must be independent of a. In R5, existence of additive inverses, which is for all a in R, there exists an x in R, such that a plus x is equal to 0 sub r, the universal quantifier comes before the existential quantifier. This means we start with an arbitrary element a in R and then find an additive inverse element x for such an a. The additive inverse element depends upon a, so for each element a, we'll have a different additive inverse element. We've already mentioned that the set of integers z is a ring, assuming the usual addition and multiplication of integers. It turns out that we can change what we mean by addition and multiplication and still obtain a ring, as in the following example. So we're going to let r equal z be the set of integers, but we're going to define a new addition and a new multiplication, and we'll distinguish these from the other addition or the usual addition and multiplication by putting a circle around the plus and the dot. And so we have this new addition, circle plus, and new multiplication, circle dot, which is defined by a circle dot b is a plus b minus 1, and a circle dot b is a plus b minus ab, for all a, b, and r, where the operations on the right-hand side of each equation are the usual addition, subtraction, and multiplication of integers. So we can show that R with these new operations is in fact a ring, but here we're not going to verify all 8 axioms, just the axioms shown, R1, R2, R4, R5, R6, and the first distributive law in R8. So for R1, closure under addition, we need to show for all a, b, and r, a circle plus b is in R. In symbolic form, we need to show the statement for all a in R, for all b in R, a circle plus b is in R. So for the proof, this is a universal statement, so we'll use a proof by arbitrary element. So we'll start by supposing a and b are arbitrary integers in R, and we need to show that a circle plus b is in R. Now remember, R is just the set of integers. So we need to show a circle plus b is an integer. Now according to the definition of our circle plus, a circle plus b is a plus b minus 1. Now since a, b, and 1 are all integers, and the set of integers is closed under ordinary addition and subtraction, then we can conclude that a circle plus b is in fact in R. Therefore, axiom R1 holds. For R2, the associative law of addition, we need to show for all A, B, C in R, A circle plus the quantity B circle plus C is equal to the quantity A circle plus B circle plus C. And this has the symbolic form shown. And for the proof, again, we have a universal statement, so we'll use a proof by arbitrary element. So we'll start, suppose A, B, and C are arbitrary integers in R, and we need to show A circle plus the quantity B circle plus C is equal to the quantity A circle plus B circle plus C. The left side is A circle plus B circle plus C is A circle plus B plus C minus 1. That's substituting for the quantity in parentheses using the definition of our circle plus addition. And now applying the definition again, this equals A plus the quantity B plus C minus 1 minus 1. And we can simplify this. This is A plus B plus C minus 2. The right side is the quantity A circle plus B circle plus C, and this is going to be equal to A plus B minus 1 circle plus C. And using the definition of the circle plus addition again, this will be A plus B minus 1 quantity plus C minus 1. And simplifying, we obtain A plus B plus C minus 2. Now, since the left and right sides both equal the same quantity, then they are equal to each other. And therefore, we have equality. A circle plus the quantity B plus C is equal to the quantity A circle plus B circle plus C. And this proves axiom R2. Now for R4, existence of an additive identity, we need to show there exists an element 0 sub r in R such that for all A in R, A circle plus 0 sub r is A. And in symbolic form, we need to prove there exists a 0 sub r in R such that for all A in R, A circle plus 0 sub r is A. So for the proof, we need to show there exists an integer 0 sub r such that the universal statement is shown is true. So the existential quantifier comes first, so we start with an existential proof. So we need to find a 0 sub r, and then we need to verify that it satisfies the two conditions. Now the element 0 sub r must satisfy, for all integers a, our propositional function a plus a circle plus 0 sub r is equal to a. Or, using the definition for our circle plus addition, this will be a plus 0 sub r minus 1 equals a. And solving this equation for 0 sub r, the a's will cancel, and we just obtain 0 sub r is equal to 1. So this tells us we should choose 0 sub r equal 1. And now we're ready to move over into the right-hand column. And since 0 sub r equal 1 is an integer, then 0 sub r is in R. And for the propositional function, we have a universal statement, so we're going to use a proof by arbitrary element. So we'll suppose a is an arbitrary integer in R, and we need to show a circle plus 0 sub r is equal to a. The left side is a circle plus 0 sub r, which is a circle plus 1, which is a plus 1 minus 1. This is using the definition for the circle plus addition, and the 1 and the minus 1 cancel, and we're left with a. And that's equal to the right side, so this proves the propositional function. So this shows that 0 sub r equal 1 is an additive identity for R under this addition. Therefore, axiom R4 holds. Now for R5, existence of additive inverses, we need to show for each a in R, there exists an x in R such that a circle plus x is equal to 0 sub r. In symbolic form, we need to show the statement shown. And for the proof, we have a universal statement. The universal quantifier comes first, so we start with the proof by arbitrary element. So we suppose a is an arbitrary integer in R, and we need to show there exists an element x in R such that a circle plus x is equal to 0 sub R. So now we start an existential proof, and we need to find an x and then verify that x satisfies the two conditions. And the element x must satisfy the propositional function, which can be rewritten as a plus x minus 1, which is equal to 0 sub R, which is equal to 1. And now solving this equation for x, take the negative 1 to the right side, becomes a plus 2. Take the a to the right side, becomes a negative a. So we obtain x is equal to negative a plus 2. And this tells us we should choose x to be minus a plus 2. So we've now found our x. We're ready to move over into the right-hand column. And to show that x is an R, we can say, well, since a is an integer, then minus a is also an integer. And so x is equal to minus a plus 2 is an integer, since the set of integers is closed under addition. Then x is in R. For the propositional function, the left side is a circle plus x is a circle plus minus a plus 2, which is a plus the quantity minus a plus 2 minus 1. Now the a and the minus a cancel, and the 2 minus 1 gives us just 1, which is equal to our additive identity, 0 sub R. So this equals the right side, so proves the propositional function. This proves the existential statement. Therefore, x equal negative a plus 2 is an additive inverse for x under this addition, so thus axiom R5 holds. Next, we have R6, closure under multiplication. For all a, b, and R, a circle times, or circle dot b, is in R. And in symbolic form, we need to show for all a and R, for all b and R, a circle dot b is in R. This is a universal statement, so we'll use a proof by arbitrary element. Suppose a and b are arbitrary integers in R. We need to show a circle dot b is in R. And according to the definition of our multiplication circle dot, a circle dot b is a plus b minus ab. And since a and b are integers and the set of integers is closed under multiplication, then we know that a times b is an integer. And since the set of integers is also closed under addition, then a plus b minus ab is an integer. Therefore, a circle dot b is in R. And thus axiom R6 holds. And for our last axiom, we're going to look at R8, the first distributive law, which states for all a, b, c in R, a circle dot quantity b circle plus c is a circle dot b plus circle plus the quantity a circle dot c. So this is in symbolic form, has a symbolic form shown. And we'll use a proof by arbitrary element. So suppose a, b, and c are arbitrary integers in R, and we need to show the equality shown. Now to compute the two sides of this equality, we need to apply the definitions for circle plus and circle dot. For any a, b, and R, a circle plus b is equal to a plus b minus 1, and a circle dot b is equal to a plus b minus ab. So to compute the left side, a circle dot b circle plus c, we compute what's in the parentheses first. So this equals a circle dot the quantity b plus c minus 1. We then apply the formula for circle dot with a substituted for a and b plus c minus 1 substituted for b to get a circle dot the quantity b circle plus c will be a plus the quantity b plus c minus 1 minus a times the quantity b plus c minus 1. So then the left side is equal to a circle dot b plus c minus 1, which is a plus the quantity b plus c minus 1 minus a times the quantity b plus c minus 1. And we can simplify this algebraically to obtain the expression shown. And we follow a similar procedure to compute the right side. So the right side is a plus b minus ab, quantity, circle plus the quantity a plus c minus ac. And this will be the quantity a plus b minus ab plus the quantity a plus c minus ac minus 1. And use some algebra to simplify this. And therefore, the two sides are equal. Therefore, the first distributive law in R8 holds. So after proving all 8 axioms, we can conclude that R equals Z under these two operations is in fact a ring. Now, if any of the 8 axioms in the definition of a ring fail to hold, then the set R is not a ring. So for example, let's let R equal O be the set of odd integers with the usual addition plus and multiplication dot of integers. And we want to show that O is not a ring under these operations. To show that O is not a ring, we just need to find one of the 8 axioms which fails to hold. In fact, the very first axiom, R1, closure under addition, doesn't hold. To show this, we need to show for all A and O, for all B and O, A plus B is an O is false. To prove this, we need to show this universal statement is false, and to do this, we just need to find one counterexample. So we can choose A equal 3 and B equal 5. Then both A and B are obviously odd, so belong to our set O. However, A plus B is equal to 3 plus 5, which is equal to 8, which is not in O. Therefore, the statement is false, which shows that the axiom is not satisfied, and thus O is not a ring under the operations of plus and dot. Now suppose we keep R equal O, the set of odd integers, but use the operations in the previous example. So for this example, we're going to let R equal O be the set of odd integers again, but we'll use the addition circle plus and multiplication circle dot defined by the two formulas shown. And the question is O a ring under these operations? We need to check the 8 axioms to determine whether or not R is a ring. So let's start with the two closure axioms, R1 and R6. R1, closure under addition, says, for all A, B, and O, A circle plus B is in O. In symbolic form, we need to show, for all A and O, for all B and O, A circle plus B is in O. So we'll use a proof by arbitrary element. So we'll start by supposing A and B are arbitrary elements of O, which means that A and B are odd integers. And we need to show that A circle plus B is in O. That is, we need to show that A circle plus B is an odd integer. Now, according to the definition of circle plus addition, A circle plus B is equal to A plus B minus 1. And since A and B are odd integers, then A plus B is an even integer. Okay, we're just going to assume our basic facts about odd and even integers in this example. Then A plus B minus 1 is an odd integer, so A circle plus B is in O. And therefore axiom R1 holds. For R6, closure under multiplication, we have for all A, B, and O, A circle dot B is in O. In symbolic form, we need to show for all A and O, for all B and O, A circle dot B is in O. And we'll suppose A and B are arbitrary elements of O, meaning that A and B are odd integers. And we need to show that A circle dot B is in O. Now, according to the definition of circle dot, A circle dot B is A plus B minus AB. And since A and B are odd integers, then A plus B is an even integer, and A times B is an odd integer. Then A plus B minus AB is an odd integer. We have an even minus an odd. Therefore, A circle dot B, which is A plus B minus AB, is in O. And therefore axiom R6 holds. Now in the previous example, we showed that the operation circle plus satisfies axiom R2, the associative law of addition, for all integers. Since the associative law holds for all integers, then it certainly holds for just the odd integers, and therefore axiom R2 holds for our set O. Similar reasoning allows us to conclude that axioms R3, R7, and R8 all hold. And note that the additive identity for circle plus we found in the previous example was 0 sub r equal 1, which is odd and hence belongs to O. It can then be shown that axiom R4 holds. Also, the additive inverse for an element A was found to be minus A plus 2. When A is odd, then minus A plus 2 is odd, so will belong to O, and it can then be shown that axiom R5 holds. It then follows that all 8 axioms hold, and hence O, under the operations of circle plus and circle dot, is a ring.